Hey everybody, it's time to start taking derivatives using some tricks and, well, some wonderful little tools that you're going to love using. So first of all, let's connect it to what we've been working on. We have been finding derivatives using the limit notation by using the limit definition of a derivative. And I want to show you how that connects with what we're going to do here by proving to you the rule for the derivative of a constant function. So if you have a function f of x equals c, so think of c as being some number, a constant, it doesn't change. So pick your favorite number and put it there. Then if f is equal to just a number, then the derivative of that is equal to 0. Another notation is the derivative of just a number is equal to 0. This is a rule that you are going to memorize because you're going to use it. Now, why does this rule happen? Well, let's do the proof. So if f of x equals, well, what's your favorite number? You can put whatever you want here. I'm going to put 5 because I have a 5-year-old. The derivative of that function, the constant function 5, we're going to find by using the limit definition. I'm going to prove to you that it's equal to 0. So the limit as h goes to 0, f of x plus h minus f of x all over h. All right, now, this is my function f of x. So how do I find x plus h? I take x plus h and I plug it in for x. But there's no x here. So if I plug in x plus h, it's still going to be 5. That's what a constant function is. A constant function means it is always 5. No matter what you plug in, the answer will still be 5. So if I continue here, write my limit as h goes to 0, f of anything, doesn't matter what I put here, so f of x plus h is 5, minus f of x, well, that's also 5, all over h. So 5 minus 5 is 0 over h. Now remember, we haven't taken the limit yet, so we simplify before we take the limit. What is a number, or 0, divided by a number? Remember, h is approaching 0. It's not actually getting there yet. So 0 divided by a number is 0. Oh, I forgot my limit notation. Put that in there. So we still have the limit. As h goes to 0, 0 over h. All right, we're not taking the limit. We still have the limit notation. We're simplifying. 0 divided by h is 0. Limit of a constant is just the constant itself. So there's your limit, which is actually the derivative of the constant function. So no matter what number you put here, if you put c in general, but c in general, c in general, it doesn't matter what number it is. If you have a function which is equal to a constant, the derivative is 0. And this is the proof. So we're going to learn some more rules. All of these rules can be proven using the limit definition of derivative. But I'm not going to do every single one. I'm going to let y'all enjoy the textbook on those. What I want to do is I want to give you all the rules and I want to show you how to use them. That's what I'm going to concentrate on. So this rule is called the power rule. He is one of the ones you will use most frequently. You'll have a bigger problem, and inside that big problem, you'll probably have one of these to deal with. So let's talk about the rule. It says, if your function f of x is equal to x to a power, so n is a power, then the derivative is this guy. What does this say? Well, the way I remember this is it says take the power down. So this used to be the power. So your power n goes down in front, and then you subtract 1 from the power. So for example, in this first one here, if I use the notation d dx, which means take the derivative of x to the 5th, well, this is x to a power. The power is a number here. Okay, you're going to have other powers later on where this doesn't apply. It has to be x on the bottom and a power up top that's a number. The derivative according to the power rule is power comes down, so that'd be 5, and then x to the power minus 1. So 5 minus 1 is 4. That's it. That's the power rule. Now, could you do this with the limit definition? Absolutely. But remember, you have to plug x plus h in to the 5th power. That means you got to do x plus h 5 times. That's a lot of work. So we need to appreciate what people have done for us is they have proven that these rules that we're going to write down work. Without that, we would be doing a crazy amount of algebra to solve these problems. Okay, let's try another one. So we're going to take the derivative with respect to x of x to the negative 1/2 power. Pause the video, try it, and come back. All right, again, does this qualify for the power rule? Yes. It is x on the bottom and then a number up top. Notice that this number is negative. That is absolutely okay. It's also a fraction, also okay. As long as it's a number up there, you're good. So what does the rule say? Power rule says the power comes down in front, the whole power, so negative 1/2. X to our new power is going to be the old power minus 1. But minus 1 is like saying 2 over 2. So we have a common denominator here. So negative 1/2 minus 2 over 2. So we put the tops together, negative 3 over 2. Now, I am okay with this, but I'm pretty sure my lab is going to want you to write with positive exponents. So let's talk about that. How would we rewrite this with a positive exponent? Well, you've already got a fraction here. So let's not make another fraction. Let's just bring this x in to join the fraction that we already have. So we already have negative 1 over 2. This x is right now upstairs. To get rid of my negative sign, this negative right here, we're going to bring x down and put him with the 2 underneath. So x to the 3/2, positive. If you want to write that as a root notation, it would be the square root with the 3rd power. That's fine, or you can leave it like this. My lab should accept this answer. Okay? So hopefully that's helpful to you. So we could do positive exponents, we could do negative exponents, but you have to have x and then a power, which is a number. So let's look at the part C here. Is this in the right format? Is this x to a power? Right now, no, it's not. It's actually a denominator, which has x to a power. It's not just x to a power. It's in the denominator, which is a problem. So we have two options. We can wait and learn a new rule later on that we can work with this the way it's written, or we can try and rewrite this. Remember who your friend is. Your friend for calculus is Mr. Algebra. Use Mr. Algebra to try and rewrite your problem into something that this rule will work for. Can you rewrite this question as x to a power? If you take the x and bring him upstairs, what would happen to his power? Should become a negative 5. These two are equal. So if I take the derivative of x to the negative 5, that's the same as taking the derivative of 1 over x to the 5th. But this one, the power rule that we talked about up here, does apply. So what does the power rule say? Take your power, put it in front. So negative 5, x to the, be careful, common mistake here, make sure you subtract 1. Negative 5 minus 1 gives you negative 6. Again, I'm good with this. You've done the calculus, but I'm pretty sure my lab will want you to write it as a positive exponent. Who goes to the denominator? Be careful here. Who has a negative exponent? Just the x. So just the x is going to go downstairs. So negative 5 stays upstairs. The x moves downstairs. Don't forget to keep his power. There you go. That would be the derivative. All right. Let's try another rule. This one's also a very important, very common rule to see when you're doing derivatives. It's called the constant multiple rule. This is kind of like what we talked about with limits. Basic idea, you have a number times a function. You have a number times a function. Whenever you have this situation, the constant multiple rule says, take that constant and just pull it out. Take the derivative of the function and then just multiply the derivative by the number. We did that with limits. Remember, we had the limit of c times the function f of x. We talked about how we can take the limit of the function and then just multiply by the constant. We can take the constant out. So same thing here. We're going to take the constant out and take the derivative of just the x part. Notice that this x part here is x to a power. So what can we use? Power rule. Okay, you're going to have to start recognizing these. Make sure you practice. So we have our 4. He's just going to multiply. He's going to chill out, hang out, while we take the derivative of x cubed using the power rule. So power rule says we do what? Pause the video, try it, and come back. Power comes down and goes in front. So that would be our 3. X to our new power. What do we do for our new power? we subtract 1. And there's your new power. 3 minus 1 is 2. Make sure you simplify to finish it out. So multiply by your constant. 4 times 3 is 12, x squared. And there's your derivative. Now, as you get better and better at these, you won't need to do all this notation. You'll do this all in one step. You'll take your power, multiply by what's in front, and you'll just write 3 times 4 is 12, x to 1 power less is 2. One step and you're done. But right now I'm trying to show you how all the rules are working together and how we technically are doing one rule at a time. Okay? Alright, so let's do the same thing here. We have our constant multiples, the negative 1/2. He's multiplying to the x. So the whole thing, negative 1/2 can come out. And we're just going to take the derivative of the rest of it. X to the 4/3. Now again, what rule do we use to take this derivative? We have x to a power, which is a number. So this is a power rule. So negative 1/2 hangs out times the derivative. So power comes down, so that's the 4/3. X to the, all right, we got to subtract 1, but we need a common denominator with the 3. So minus 1 is minus 3/3. 4 minus 3 leaves us with 1/3. Wrong color. Oh. Multiply your fractions straight across, or you could reduce. Let's see, 4 and 2. So they both are divisible by 2. So 1 and 2 if we divide them by 2. So multiply across. So negative 1 times 2, negative 2. 1 times 3, 3. X to the 1/3. Or you can write that as the cube root of x. There you go. All right, let's put one more rule, and we're going to bring it all together into one cool problem. So this one's called the sum rule. This says if you have the derivative of two functions added together, u and v are something we use a lot in derivative notation because it helps us shorten our work. So think of u as f of x and v as g of x. They're representing functions, but this shortens the work. So if you have the derivative of two functions adding together, don't do it as one big problem. You break it up. You do the derivative of each term separately and then add them together. Which means that this much larger problem here, y equals 6x cubed minus 5x plus 10, we can do as 3 separate problems. Each term will be its own problem. Which, if you look at it, the first one, it has a power of x and then a constant in front. So we're just using the rules we've already done. We're just breaking the big problem up into small rules so that we can use what we've been working on. All right, notation. So y, we want to take the derivative of. So there's different notations you could use. Y prime or the dy dx. These are two different ways to denote the derivative of y. You have to know both just so you can recognize it in MyLab, but when you're writing it down, denote it either way you want. All right, first term, 6x cubed. What does the 6 do while we take the derivative? He's a constant multiple, so he's just going to chill out while we take the derivative of the x cubed. X cubed is just a power of x, so here we're going to use the power rule. So power rule says power comes down, so 3 comes down, x to 1 power less, so 3 minus 1 leaves us with 2. Don't forget to multiply the 6 and 3 together eventually. Minus the 5 is a constant multiple, so what does he do? He chills out while we take the derivative of x. Let's think about this. X has a power of 1 if you don't see the power. So what does the power rule say we need to do? The power comes down and we do 1 less for the power. That's interesting. So we have 1x to what power? The 0. X to the 0 is simply saying there are no x's left. So this is really just 1. So the derivative of just x is equal to 1. And that's something you might want to memorize, but the power rule does get you the right answer as well. Okay, so we have the negative 5 chilling out. The derivative of x is just 1, so 5 times 1. Or you don't even have to write it because you have the 5 sitting there. Plus, what's this last one going to be? He is a constant. What is the derivative of a constant? Do you need to go back and look? Derivative of a constant is 0. Right? So those are the rules that we've worked on. Bring them all together and we're able to do much larger, more interesting problems. Simplify your work and see what you have. So 6 times 3 is 18, x squared minus 5, and everything else is done. There you go. That's your derivative. Let's try one more. So we're going to take the derivative y prime of this function. So let's look at the first one. Remember, we're going to do each of these terms separately. So we have 4 problems here. First one, what rule are we going to use? There's no number in front. We don't have to worry about that. Power on x. Okay, power rule. So power rule says we do what? Why don't you try this whole problem, pause the video, and come back and see how it works out. All right, you ready? Power rule. Power comes down. X to 1 less. So if I do -5 minus 1, that would be -6. Be careful with your signs there. -1/2 is a constant. So he's just going to chill out while we take the derivative of x squared. So the derivative of x squared. 2 comes down, x to the 1 less, so 2 minus 1 leaves us with 1. Plus, we just talked about this. What's the derivative of x? Just 1. The x's are all gone. What's the derivative of -pi? Well, -pi, remember, pi is what? He is a number. So he is actually a constant. What is the derivative of a constant? 0. You don't have to write that. I'm writing it to make sure everybody understands where it went. The derivative of a number by itself goes to 0. That is not the same as a derivative of a number times a function. That does not disappear. So be careful. They're 2 different things. If the number is by itself, it goes to 0. If the number is multiplied by a function, that number stays. Simplify, let's rewrite it. So first of all, the first term has a negative exponent. How would you rewrite that? -5 over x to the 6. You'll have to experiment in your homework. It may accept negative numbers eventually, but if it says rewrite your answers with positive exponents, make sure you obey or you'll be marked wrong. All right, the second term we can simplify because we have a 2 in the denominator and a 2 in the numerator. So that would be just negative. We don't need to write the 1, it's understood. And then an x. We have a +1 and the 0 is gone. All right, those were a lot of rules. Those were a lot of examples. Make sure you practice. That is the key to doing well for derivatives is practicing. These might seem easy, but if you can really get these down pat, it'll make the rest of the derivative rules that we're going to study much easier. This is the foundation. It just builds from here. So you're going to need all of these as we go through. So as usual, steady heart, and I'll see you in the next video.